All right, today we're going to be talking about linear functions, nonlinear functions, and function notation. So the first thing we're going to talk about is what is a linear function? Well, first off, a linear function is indeed a special function. So what that means is that every domain, remember that's an x variable, every domain maps to exactly one range. So just because it's a linear function, it has to first be a function. Then the thing that separates it from being a linear function is that the graph of the function is a line. Okay, if you think of the word linear, it sounds like line. So the graph of the function is a line. Okay, there are some questions that we ask to determine whether it's a linear function or not. The first question you should ask is it a function at all? Does each domain map to exactly one range? If it is not a function, then it definitely cannot be a linear function. It can be a line still, it just cannot be a linear function, but it only can be one type of line actually. Okay, the second thing is if I give it to you in a graph, so let's say you're looking at an actual picture, and the first thing you should ask is, number one, is it a function? Number two, does the graph make a line? So when you look at the picture, is it an actual line? Number three, if you're given to it in chart form, okay, or a set of ordered pairs or something along those lines, a t-table, is there a common ratio? Now, what that means is that your change in y over your change in x. Now, remember, when we change, we simply go high minus low, high minus low. So what we're looking for there is that is common between any two given points in the chart or the ordered pair. Okay, now if there is a common ratio, then it is linear. If it is not a common ratio, then it is not linear. It still can be a function, it's just not a linear function. All right, so let's give it a shot. So let's start here on this first one. It says, is it a function? So remember the test that we use when we see a graph is we take a vertical line, and when we take that vertical line and we drag it across our graph, if you notice, at any one point, I am only hitting 1 point on that graph. So when we look at this, we would say, yep, this is a function. Then I look at this and I say, okay, it is in the shape of a line. So we would call this a linear function. Okay, so now let's take a look at number two. So if I take number two and I come across this graph, so I take this and I start moving across, you'll notice that I only hit 1 point at any time going across that graph. So yes, it is a function. Then I ask myself, is it in the shape of a line? And the answer would be no, it's in the shape of a V. So we would call this a non-linear function. All right, so let's keep trying then. Let's take a look at number three here. So we'll scroll back over. If I look at three and I take this line and I go across my graph, my vertical line test, you'll notice you're not hitting any more than 1 point at a time. So this is a function. And then I look, and if I take those points and kind of imagine what they would do if I connected them, it does form a line. So this is a linear function. Okay, let's take a look at this last one then. So number four, I start to go across. We have a problem. Here we hit definitely more than 1 point on that graph. So this is not a function. So it is a vertical line, but it is not a function. Okay? So when we look at that, that's how we test it given a graph. The next set of examples that we have is, what if we do it using a chart? Okay, so we start in and we say, okay, is it a function at all? Okay, so I look, remember to determine the function off of a chart, we look at the x values. All of my x values do not repeat, so we would say, yep, that is a function. Yes, it is. So the next thing I'm looking for is a common ratio then. So what I'm going to do is I'm going to just do some basic subtraction here. So I'm going to go 2 minus 1, that's 1. 1 minus 0, that's 1. 0 minus negative 1, that's 1. Then I come back and I go 5 minus 3, that's 2. 3 minus 1 is 2. 1 minus negative 1 is 2. So when I look at this, the ratio of the change in y was 2 over the change in x. So if you notice, every single one of these pairs has that exact same ratio, a 2-to-1 ratio. So that would tell me that this is a linear function. Okay, let's try the second one. So I start off and I say, okay, are you a function? So I look at my x values. I look across, none of them are repeating. So therefore, yes, it is a function. The next thing I check now is for my common ratio. So 3 minus 2 is 1. 2 minus 1 is 1. 1 minus 0 is 1. Then I come down. 9 minus 4 is 5. 4 minus 1 is 3. Uh-oh, we have a problem. This ratio would be a 5-to-1. This ratio would be a 3-to-1. So they do not have a common ratio. Since they don't have a common ratio, we would say this is a non-linear function. Okay, linears, remember, have to have a common ratio. All right, let's take a look at number 7. So when we start off, the first question we ask, is it a function? So I look at my x values, and as I go across, I see something that's repeating. So the question is it a function? No, because -1 repeats in the domain. Okay, so since -1 is repeating in the domain, that is not a function. Okay, so we don't even go any further with that. The last one we have is we start again and we say, okay, is this one a function? So the first question I ask is I go across my x's, none of them are repeating, so I would say, yes, that is a function. The next thing we check is we check our subtraction. So I'm going to start with my x's. 1 minus 0 is 1. 0 minus -1, that's a 1. -1 minus -2, that's a 1. So we're on a right track. -3 minus 0 is -3. 0 minus 3 is -3. 3 minus 6, that's -3. If I notice, I have a combination of a common ratio of -3-to-1 on all of these pairs. So therefore, that would be a linear function. So that's how we do that based off of a chart or graph. All right, the next thing we need to talk about is this thing called function notation. Function notation is just a fancy way to write an equation for a function. So by writing it in this manner, you are saying that that equation represents a function. Remember, a function means that every domain maps to exactly one range. So we are saying that by writing f of x in function notation. Now, all we simply do, the way it looks kind of funny, but all they simply do is they take the f of x and they write that for the range variable. Now, if you think back, what is normally the range variable? The range variable is normally y. So all they're doing is they're taking the y out and they're putting the f of x in. Okay, so in a normal equation, the y is our range and the x is our domain. Well, in function notation, the f of x is my range and the x is my domain. So you might be asking, then why do we write it like that? Well, it can change. We can use different letters to represent the different functions. But also, when you look at this, the f of x, what that simply means is the function with the name f with the domain variable of x. So when we do this, when we write this x, this inside that grouping, that is telling me, hey, this is going to be your domain variable, okay? So it's saying the range, f of x, is the function of f with the domain variable of x. Okay, now we could use all kinds of stuff. We could do g of x, h of x, we could do m of n. Now when you think of that, that would just be the function of m with the domain variable of n. Okay, now when we go into the next part, it's going to ask us to find the range. And when we do that, we're just simply going to plug the x value in, and we're going to solve it for f of x. If they're finding the domain, I'm going to plug the f of x value in, and I'm going to solve it for x. All right, so let's take a look. If you notice here on this first one, it says f of 4. Normally, that's an x. So we're just going to take that and replace that with the x. So it'd be 5 times 4 minus 3. So 5 times 4 is 20. 20 minus 3, that is 17. Now, what did you just find? What you actually just found was an ordered pair, 4, 17. Okay, that's what you actually just found. The next one that we have is we have a negative 2. We're just going to plug that in. So we go 9 minus negative 2. Remember, subtracting a negative becomes adding a positive, and that would give me a value of 11. On this next one, they're telling me the domain is 6, so I'm going to plug that in, and that gives me 3 minus 4 times 6. So 3 minus 24, which is negative 21. All right, now on the next part here, this time they're giving me the range value, and I need to find the domain. The way I notice this is they say f of x is equal to 9. So I'm going to take the 9 and plug it in where I see the f of x. So 9 equals 3x minus 6. Now at this point, we're just going to solve it like we have been. So 15 is equal to 3x, divide by 3. So x equals 5. Okay, let's try that again. We're going to take the negative 9, plug it in for the g of x here. So negative 9 is equal to negative 2x minus 3. So I'm going to add 3 to both sides. So I get negative 6 equals negative 2x. I'm going to divide by negative 2, so x is equal to 3. And in this last one, it says f of x equals 15. I'm going to take the 15, plug it in for the f of x, and then I simply solve again. So I would minus my 12 here. I get 3 equals negative x, divide by negative 1, so x equals negative 3. Okay, so that's how we use function notation to find the domain and range values. Now, what is this going to look like on a graph then? So what we do is there's 2 ways we can write this. I wrote it as y equals. You could also write this as f of x. So over here, if you wanted to, you could write f of x is equal to 2x plus 3. And then what you notice is they give me a bunch of domain values. So all we're simply going to do is we're going to take that negative 1, we're going to plug it in. So it'll say 2 times negative 1 plus 3. Then you're going to go 2 times 0 plus 3. And you're just going to keep going. 2 times 1 plus 3, 2 times 2 plus 3. So, and then you just work those out and get those values. So 2 times negative 1 plus 3, that's going to get me a value of 1. 2 times 0 plus 3, that's going to give me a value of 3. 2 times 1 plus 3, that's going to give me a value of 5. 2 times 2 plus 3, that's going to give me a value of 7. Now, what you just found is 4 different ordered pairs. So now we plot them. Remember, the x value is the horizontal left-right movement. The y value is the up or down movement. So when my first one says negative 1, 1, that means I'm going to start at the origin, at the center of the graph. I'm going to move left 1, up 1, and I'm going to put my point. My second one is 0, 3. So I'm not going to move left or right any. I'm just going to move up 3. And then my third one is at 1, 5. So I'm going to move right 1, up 5. And my last one is 2, 7, right 2, up 7. At that, I'm going to connect my dots into a line. And I'm going to draw my arrows on the end because that line continues forever. So if you look at the last 2 slides, we're basically doing the exact same thing. It's just how it's presented to us. So on this one, let's try again. We're going to take our x's, we're going to plug them in. So the first one is 6 minus negative 2, 6 minus negative 1, 6 minus 0, 6 minus 1. So when we go 6 minus negative 2, remember that's plus a positive. So that would go 6 plus 2, which is 8, 6 plus 1, which is 7, 6 minus 0 is 6, 6 minus 1 is 5. So remember, first number, the x value is the left right, the y value is the up down. So we come over left 2, up 8. Then I go left 1, up 7. Don't go left or right any, up 6. And then I go right 1, up 5. I take that, I connect my line. And then at that point, I just draw my arrows on the ends, and there's my linear relationship. And that is what we talk about with linear functions.